Okay, hello. This is going to be a video on the power rule. The power rule, I've used it a couple times in previous videos for simplification, just making things quicker instead of having to write the whole thing out. I didn't use it in any of the proofs, so don't worry if you think that, um, don't worry like that you needed to know this to do those past two proofs with the constant multiple rule and the sum rule. Um, So don't worry about that. I just used it in the examples just to make it quick. But I'm just gonna be proving it today for any of those who don't know it. Um, you do use it a lot, just like the other ones I've proved. But it's really important to understand what you're doing, because as people learn this rule, they tend to forget. Um, they tend to forget what it means, and they just kind of do it without understanding what they're doing anymore. So just know to kind of revisit this every so often if you ever forget it. It's really important. You use it a lot. I guess that's all I can say. But before I do prove it, I'm gonna start off just by giving a couple examples here. I'm gonna say if you want to find, or if you want to factor, I'm sorry, if you want to factor this expression, a squared minus b squared, hopefully you know that that's just going to be a minus b times a plus b, right? This is something hopefully you've learned. If not, I recommend go to learn about that. It's not really complicated. The middle terms just cancel out. That's all. If I want to do a cubed minus b cubed, it'll be like this: a minus b, and then a squared plus ab plus b squared. And if you want, you can check these if you want, or if you feel like you need to. Um, I I encourage you to just to have a better understanding. And I'm gonna do one more here, or I'll do two more, but one more with a real uh, value. So we're gonna do a to the fourth, b to the fourth. Okay, and then this is gonna be a minus b. You might see a pattern here, hopefully. If not, I'll explain it in a moment. All right, and again, if you want to, just go ahead and expand these out yourself. Make sure they're true. All that. Just work through it yourself. Okay, so right off the bat, you should notice that they all start with a minus b, right? That's in all three of them here. Now, you might also notice that look at the power here. We have squared, cubed, and then to the fourth. If I were to write this expression right here, a plus b, if I were to write that, I could write it like a to the 1, b to the 0, plus a to the 0, b to the 1. If I wanted to write this one here, I could say a squared, b to the 0, plus a to the 1, b to the 1, plus a to the 0, b squared. If I want to write this one, I could say a cubed, b to the 0, plus a squared, b to the 1, plus a b squared, plus, I'm sorry, a to the 1, a to the 0, b cubed, and that's that. So you might notice a pattern here. Typically, when we deal with binomials like this, you come across these patterns, and they are related to the binomial theorem and Pascal's triangle. I'm not going to go into that right now, but just take note here, as when you start at a squared, right, you're going down 1 each term, and b is going, the power is going up 1 for b each term, and the power is going down 1 for a each term. So you start at your highest on a and your lowest at b, and you end on your lowest of a and your highest power of b. Now, this can be expressed, since we have this a minus b here, this can be expressed as a minus b of a to the n minus 1 times b to the, well, I guess it starts at 0, right? Then your next term is going to be plus a to the n minus 2, b to the 1. And then this is going to keep going, and I'll move this in a moment here. And what eventually, if you have n power here, right? If we're looking at this right here, we have a power of 2. If you want to generalize this for a to the n minus b to the n, this is what that is. I'm writing it right now. So then we're going to have dot, 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 and we know our end is going to be a to the 0, or we could write it as n minus n, right? Because that'll be our last term there. I'm going to write it as 0 just to save some space. And then we'll have b to the n. It'll be at its most highest power, right? So that's what that is, okay? Now we're going to employ this in this proof here. I know that looks like just a lot to take in right now. Let me take this and move it over here so you know that it's not related to those other ones. I mean, it is, but I'm going to write a to the n minus b to the n. Okay. Just so you know that that's what that is. So this is a general term for all of these, and you can apply it to any of these, and you will get these. That's what these are. Okay, so now that you know that, now we can jump into this power rule. So let's start with writing the difference quotient. So let's say the limit as delta x is approaching 0, we'll have f of x plus delta x minus f of x over delta x. Okay, so what I want you to recognize here is we're going to consider this first bit here. Let's say that we have this as a and this as b. Or actually, here, I made a little bit of a mistake here. If it's a power function, we know it will be something like this. We know it will be written something like this. It'll be x plus the change in x, delta x, raised to the nth power, right? And then we're going to have minus x to the nth power. That's just the difference quotient, okay? And then over delta x, okay? So what we have here, we're going to consider our first bit here a and our second bit here b. So if we want to write it in this format here, we can. So that's exactly what we're going to do. So a we know is x plus delta x, and b we know is x, right? So minus x. Now, obviously, you can subtract these. I'll do that in a moment, and you'll be left with just delta x, but I'll do that in a moment, so hold on. If we keep moving forward, a to the n minus 1, well, that's going to be x plus delta x. I should really write these in double parentheses. X plus delta x to the n minus 1 times b to the 0, so times 1, right? No matter what it is, it's going to be 1 here. So I might as well just not even write that. All right, so then what we're going to have is we're going to have plus a to the n minus 2, so x plus delta x to the n minus 2, and I forgot, actually, copy, paste, boom, right here. This is a limit, so yeah, don't forget that, I already did. Okay, and then our b is now going to be b to the 1, so now it's just going to be times x, so I'm going to write x here. Okay, and I'm going to move this down here, actually, just to get some space. Okay. Now what we have, I'm going to put dot, dot, dot here, just to show that we're kind of skipping to the end. And we're going to have x plus delta x to the, let's say, I guess to the 1, really. And then we'll have, I'll explain that in a minute, x to the n minus 1. This is 1, by the way. And then our next term, I'll explain this all in a second. I know it may be a little bit confusing here. And then our next term is going to be plus delta x to the 0, and then x to the n. Okay, so close parentheses. So this is a little bit, quite a bit to take in. Okay, right off the bat, actually, here, remember that this is all over delta x, because what we did, we just rewrote the numerator here into this. So what we did here, right off the bat, we know x minus x cancels. So I'm going to go ahead and do that. And I'm just going to go ahead and, I don't have space to write this again, really. So I'm just going to rewrite it. So then we're going to be left with delta x here. Right? And then we have delta x down here. So these actually cancel. So this will all be over 1. If I delete this, I can delete this entire fraction. And I'm going to move this over here. Okay. So we're left with just this. Okay. So what can we make of this? If you look at this, like I said, this part here I'm going to explain right now. So the reason I say x plus delta x to the 1 is because if you remember, if we're starting at our highest power here for a, and if this is our last term, one term away from that, on our last term, we know it's going to be to the 0. So I just said to the 1 here, right? We can assume that that's going to be to the 1 because that's just how this works. If you have any questions about that, let me know. And the reason I said x to the n minus 1 here is because that is just before, and I really should put this x to the 0 here. I'm sorry about that. That is just before our last term, right? So our next one, it will be n. Oh, I'm sorry. No, I made a mistake here, actually. Yeah, no, this is going to be n minus 1. Yeah, I'm sorry. Yeah, forget that. Here. Yeah, I'm confusing myself with something else right now. N minus 2. Yeah, okay. This will be our last term because this is our highest degree we can have here because we had the other ones multiplying into it, remember? So now what we can say, yeah, I'm sorry about that. Now what we can say is the following here. Okay, if we look at this, x plus delta x to the n minus 1 times x to the 0 is just going to be x plus delta x to the n minus 1. Okay. our next term, x plus delta x times n to the negative 2, or n minus 2 times x. Okay, well, that's going to be x plus delta x to the n minus 1, right? Okay, and then what we're going to have, if we skip over here, dot, 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 whatever, we're going to have plus x plus delta x to the 1 times x to the n minus 2. Well, that's just going to be x plus delta x okay, this is true. What I just did was true, but I think it may be a little bit confusing. I can do this in a better way. Now I'm doing this as I go. I'm trying to remember off the top of my head. Since delta x is approaching 0, we can just cancel all these. So let's just do that right now. I know this is a really scuffed proof because I've made a lot of mistakes in this, but it'll turn out okay. So just bear with me here. Okay, so there's no more delta x's. They all approach to 0, right? There's nothing stopping them because it can't be divided by 0 anymore because we already factored that out and it canceled. So really this is x to the n minus 1 times x to the 0 plus x to the n minus 2 times x dot 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 plus x to the 1 times x to the n minus 2 plus x to the 0 and then x to the n minus 1. Now what you'll notice here is actually all of these multiply to be x to the n minus 1. When you multiply these together, it's x to the n minus 1 because this is just 1. X to the n minus 2 times x is x to the n minus 1. X times x to the n minus 2 is x to the n minus 1. X to the 0 times x to the n minus 1 is x to the n minus 1. How many x to the n minus 1s do we have? Well, we have n times x to the n minus 1 of these, right? That's how many we have. We have n of them. That is the power rule right there. Now I know this proof was kind of scuffy. I know the other proof I did for this before I'm redoing these, I actually think that this one's easier to understand. I think I may have conveyed it a little bit, may have made it a little bit too complicated than it is. But the other one, it involves the binomial theorem directly into it, and I didn't really explain what it was. So I think this is a much more appropriate proof. If you can get past all the errors I made, hopefully you can understand what I'm saying here. And again, if you have any questions, let me know. But before I end that, I want to use this. So what I'm going to do is copy this and let's use it. So let's make an example. Let's say we have x cubed and we want to get the derivative of this. So d over dx of x cubed, right? Okay, well, x cubed, we have x here, right? We're plugging it in. So x to the cubed. 3 is n, right? So if 3 is n, what we're doing is we're bringing that 3 down right here. You see 3 here? And then our exponent is 3 minus 1, so it's 3x squared. Okay, so that's a pretty simple little demonstration there. What if we have 2x cubed? Well, it's the same idea, but now we have this 2 on the outside. We're using the constant multiple rule here, if you remember that. It's the same thing. Think of 2 as k here. This is what I said. You use it without even knowing. And then you have your n here. So we're going to have 3x squared. Like we just made that, right? Multiply that in. We have 6x squared. And I think I actually used this example in the other video, but that's where it comes from. So that's why all of these kind of intertwine here. Now, what I'm going to do is I'm going to do like a compound usage of all the ones we've proven so far. So if I delete all this, let's say I want the derivative of, let's say I want the derivative of x to the fourth power plus x, or plus 2x cubed minus x squared plus 10x minus 22. Okay, I just made this up. There's nothing special about this. Okay, so this is going to be a combination of the sum rule, the power rule, and the constant multiple rule. So if we look at this, let's start at the very top. The sum rule tells us that all of these will be split into their own derivative. The derivative of a sum is the sum of their derivatives. So what I'm doing here is I'll take this, copy, paste. I'm going to take this plus, I'm going to just go ahead and write this out really quickly, plus, and here we have 2x cubed d over dx of x squared d over dx of 10x, move this to the side. And if you want, go ahead and work this on your own. Hopefully you see where I'm going with this. And then we're going to have minus d over dx of 22. Or I could say plus -1, which is what I'm going to do. Because if you remember, the sum rule is talking about sums. This is a negative. So I could just rewrite that as the sum times this negative number here. And it works the same way because of that constant multiple rule. Think of this -1 as your constant. Anyways, so, and then 22. Okay, so this is very long and tedious. When we actually get down to doing it, it's pretty quick and easy. When you're doing these in the field, though, you don't need to do all this. You'll have it down at that point. You don't have to write all this out. You'll be able to go and look at each of these, boom, 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 and you'll be done with it. And just rewrite it out like that. I'm just writing this out so you can understand how all of these rules are in play here. So what I just showed you was the sum rule in work here. Okay, so then what we're going to use for this first one is the power rule, which will be 4x cubed. Over here, we have 2x cubed. Like I showed you earlier, what we're going to have here is that 2 for that constant multiple rule times the derivative of x cubed, right? It's the same as that, all right? And we know the derivative of x cubed is going to be 3x squared. So 3x squared. We just did this. All right? These multiply together, and we get 6x squared. Over here, we have plus the derivative of x squared. Okay, derivative of x squared, power rule, 2x. Plus the derivative of 10x. Okay, power rule, 10. Plus -1. This is the constant multiple rule, kind of, sort of. And then you have d over dx of 22. And the derivative of any constant is 0. So we have 0 times -1, 0. So plus 0. And in case you're wondering why the derivative of any constant is 0, just think of a graph and think of a flat line, right? Let's say we have y equals 2. That's just going to be, if we were to write that in the difference quotient, right? What we're going to have is 2 minus 2 over delta x. And the reason I did this is because no matter what x position you're at, it will always be 2. So when you say x plus delta x, it won't make a difference. It'll always be 2. So you're going to have 2 minus f of x, which is also always going to be 2. So your numerator will always be 0, no matter what delta x is. So that's just a quick way to explain that in case you were wondering. Anyways, this is our answer. So we can get rid of this. We can drop this 0. And we're just left with this. So that is your answer to this question here. That was kind of a little bit complicated. I just wanted to show you how all of these rules intertwine, and you can use them all, and you can combine all of them to solve these problems. So going forward, you're going to learn more and more of these rules, and you'll be able to employ them in different ways to solve even more complicated problems. So yeah, that is the power rule, its proof, and how to use it. Thank you for watching.